Swayam Prabha. Digital India. Educated India.
Our last discussion, we looked into how sensitivity to decision function can result in different choices. To quickly recap, last time we looked into this problem of earth dam site selection, where we were deciding between two sites, site A and site B, where both sites were having different benefits, but both of them were susceptible to earthquakes. We would not know in many cases that how loss would depend on number of earthquakes happening. So we tried different loss functions, started with linear, then we also tried c raised to power x form, and then also looked into that if expected loss function looks like L equal to 5x square, how our decisions are going to change when we have to make a site selection. If you quickly recall, we tried to do expectation of loss function E equal to Cx, where we wrote it as 5x square Px and summed it all the way from x equal to 0 to infinity, because we do not know how many earthquakes can happen. So, theoretically infinite earthquakes are possible, but when multiplied by the Px itself can be fairly low, and that would act as weighing that particular number of earthquakes to a much lower value. And then we followed certain mathematical operations, since it is x square, and when we do expectation of x square, we should get a functional form which is a function of variance of x by definition of variance, and then we realize that the cost function is 250 times parameter plus 12,500 parameter square, and then based on the parameter values that we were given that two parameters are possible with 50% probability at each of the sites. All we did is we plugged in those particular values to calculate our loss functions, and then we saw that as our loss function changes, our decision can change from site A selection to site B selection when losses are brought into picture. Now, in this entire information, everything was given to us in terms of either parameters were known, and we have to construct simple decision trees, put it into our loss function, calculate the expected losses, and go ahead with the decision. However, in many cases in real world, what may happen is that we may also have both discrete as well as continuous random variables coming together in a same decision problem. So we have to find a way how to deal with that in this framework of prior analysis. Please understand that whatever discussions we are having right now, every information is ready-made available to us. That is, all the parameters and even functional forms are available. Data has already arrived and we are making decision based on data. Hence, we call this as a prior analysis. In subsequent modules, we will also look into something called as terminal analysis, that you have made a decision and then new data streams are coming and you have to update your decisions that you have made a priori, how you would account for those new data points into updating your decision. But even if I am combining continuous variables with discrete, discrete with discrete and so on, I am still using information that is available a priori, either coming from the field or experiments or from the experience, and no updation is happening in this particular case. So let us look into this particular problem. It says that this is a decision problem for a construction project. Suppose that there is a site where some construction is going on. However, contractor now only has 30 days left before the project's scheduled completion date happens. In next 30 days, anything can happen. That is, weather can be good, it could be bad, or it could be excellent. All these contractual obligations, they also have some financial commitment involved. So, for example, if contractor does not oblige by the deadlines already committed, there may be certain penalties that may be imposed by client, because contracts are legal documents. So, what contractor has to do, they have to meet the deadlines once they have agreed, entered into this particular agreement. So, they may have to expedite the particular project. How an expedition will happen in any project? More resources needs to be mobilized, and resource mobilization involves the cost, and it would be cutting from the profit. So, resource mobilization, although seems easy to say that yes, let's get more machines, more laborers or more engineers on the site, but there are cost implications involved. Hence, it has to be an informed decision from the contractor side, so that they are at the end making net profit. Even if deadlines are missed, they may have to pay penalty, but if the cost of penalty is way higher than cost of mobilization, then of course mobilization is beneficial. However, if cost of mobilization is, let us say, 5 times more than the penalties itself, then contractor may decide other way around, that okay, I can pay penalty, and as far as the legal clauses permit, I would be okay to give up the profit in terms of fine rather than mobilizing the extra costs. And this is exactly what decision making is, that two sides are poles apart, and costs are involved on both sides. So, in this particular case, what happened is that there was a bad weather in first phase of the project, as a result of which construction has been progressing at unanticipated rate. Now, based on the contractor's prior experience and judgment, see, I use the word prior, and hence this entire framework is prior analysis. Based on the contractor's judgment, the project could still meet the deadline if exceptionally good weather prevails in next 30 days. And he estimates that this may occur with a 20% probability. So, now odds are against the contractor, because there are only 20% chance that weather is going to be exceptionally good, and timelines will process as things will happen. And here you can clearly see that we are combining uncertainty with decision making, because now lot of other random variables are also going to come in picture as we go forward. Now, if normal weather prevails, his experience says that completion would be delayed with the mean of 5 days and standard deviation of 3 days beyond scheduled completion date. And if bad weather continues, the corresponding mean and standard deviation of delay will be 15 and 5 days respectively. And we can assume that normal and bad weather conditions are equally likely to occur, and the cost of delay is 0.1 x square plus x in thousands of dollars, whereas x is the length of delay in days. Again, let us look into boundary conditions. If x is equal to 0, you are not going to pay any penalty. If x is a very large number, you are going to pay square of that multiplied by some scaling factor plus a linear cost involved with addition. So, as the number of delays will progress, the penalty may actually be greater than the profit that contractor is expecting from that particular agreement. Hence, it has to be done very thoroughly. Also, it is further stated that the contractor has an option to launch a crash program. So, they can deploy more resources at an additional cost of $10,000. With the crash program, he anticipates that the chances of completion of project on schedule in the case of normal and bad weather would improve to 90% and 70% respectively. Also, if delays does occur even after crash program, their mean and standard deviation will be reduced by one day. So, if you see that initially we were having delays of order of 15 days, even with that 15 days there was an uncertainty component of plus minus 5 days. Now, the contractor expects after crash program, after resource mobilization happens, there is high probability that construction will be completed on time. However, even if he misses the deadline, the delays would be 15 times lesser than what was actually going to happen if bad weather prevails without resource mobilization from 15 days to 1 day. And of course, that uncertainty still prevails, that even 1 day can be plus minus 1 day, 0 days to 2 days on an average. Again, in absence of any other information and with only mean and standard deviation given to us, we would start looking into the delay distribution as normal distribution. We have already looked into that, and then try to find an answer for the contractor, that should the contractor be launching the crash program at additional cost of $10,000 or not. So, what we will do here, first of all, there is too much information that we have to handle. We will tabulate entire information that is available to us. So, first of all, we will try to extract the useful information, and we will try to develop certain table for that. Here I am going to have two sides of this entire table that I am going to make. On one side, I am going to write without crash program, and on another side, I am going to write numbers with crash program. So, without crash program, and here three possibilities are there, that weather can be exceptionally good, weather can be normal, and weather can be bad. All these three possibilities are also there even when crash program is launched, because contractor has no control on weather, he can only control the resource mobilization. So, good, normal and bad. As stated in original question, chance of happening weather is good being 20%, and other two possibilities are equally likely. So, 40% chance that it would be normal weather, 40% chance it is going to be a bad weather. Again 0.2, 0.4 and 0.4. So, we have sort of converted lot of information given to us in one of the rows in that particular table. Now, next thing is probability of timely completion. When weather is good, contractor is 100% sure that project will be completed on time. So, we will assign this number as 1.0. When weather is normal, he says that it is some function which I have to infer from the normal distribution delays, but it is not just a number I can put like 30%, 20%, it has to be calculated from probability distribution function that is given to us, and similarly here we will have f of 2. When weather is good, chance of this is happening is 1, right, and when crash program is launched, he is 90% sure that there would be no delays. So, we would have 0.9, there are no delays at all. However, 10% uncertainty still exists there, and it would have certain parameters, and says that mean and standard deviation of delays are going to be 1. So, this becomes expected x, this becomes standard deviation of x. Similarly, when weather is bad, contractor envisions that 70% chance with crash program he can still complete the project, and 30% chances are there that delays will be there, but still 1 and 1 days of delay will happen. Now, you see that if you look into with crash program side, we have been able to add lot of realistic sense here, that is compared to normal and bad, the confidence of timely completion has reduced, but still better than crash program, where delay is now guaranteed, that if there is no crash program and weather happens to be bad, which has more chances than good weather to prevail, that delay is imminent if crash program is not launched in that particular case. So, when weather is good, the expectation of x and standard deviation of x does not apply, because there is certainty, and and deterministic processes does not have their means and random and standard deviations associated with them. So, we do not need that information. When we talk about normal weather, expected delay is of 5 days, standard deviation is 3 days. When weather is bad, we have delays of 15 days and expectation and standard deviation around x is 5 days. Also delay cost is given to us, which is given to be 0.1 x square plus x. Now, with this information, we can say that if cost function is EC, expected cost of x is expectation of 0.1 x square plus x, which is equal to 0.1 expectation of x square plus expectation of x, using the properties of expectation that the expectation of EC x is equal to c times expectation of x. Just move it here and so on. Now, if you recall, expectation of x is nothing but mu itself. Expectation of x square is expectation of x whole square plus variance of x by definition of variance, because variance of x is expectation of x square minus expectation of x its whole square. So, expectation of x square can be worked out simply like that. So, now we can again look into the numbers of mean and standard deviation and put them into some better sense, that when we do not have crash program, that is without crash program, and we have with crash program here, right. Crash program simply means more resources in this particular context. So, the cost without crash program when normal weather prevails, and in that particular case is simply 0.1 into 25 plus 9 plus 5, which gives us value of 8.4, right, using B, and this I would call as A. Cost of crash program when bad weather prevails is 0.1 into 25 plus 22 plus 15, because this becomes 15 and 5, square of 5 becomes 25, square of 15 becomes 225. So, that is why I have 25 plus 225, not 22, but 25 plus 225 plus mean added, which was A, and this entire term is multiplied by 1. So, 0.1 first value substituted here and second value is substituted here. So, just highlighting. So, here we substitute square of x, which was 5, and then we also have the variance substituted here. Sorry, so we get the square of mean, which is 15 days was the mean delay, square of 15 is 225, and variance of x, variance standard deviation was given as 5. So, square of 5 comes out to be 25 plus 15, which again is given to be the mean in this particular case. So, this number in first case comes out to be 8.4, in second case it comes out to be 40. You can check these calculations for yourself. What is more important is the concept itself, that how we are bringing in the randomness associated with x into our overall decision making framework. Now, when we talk about with crash program, cost with crash program, this is the expected cost. We have not added 10,000 component yet. We will do that when we make the decision tree. We are right now just working on the expected cost of x focused around the delay. The cost of crash program itself we will worry about later. So, in this case cost is given as 0.1, mean is 1, standard deviation is 1. So, square of 1 and 1 plus 1 gives to be 1.2. Similarly, cost of crash program when bad weather is given, excluding the cost of program itself, but only in terms of delay, again comes out to be 0.1 into 1 plus 1 plus 1 0 based on the parameters that have been given to you. You can always argue that how the delays even with crash program can be same when weather is bad or weather is good. But this is where prior information analysis has its limitations. We can only infer decisions based on the information that has been given to us. If we really want to update that particular information, we have to observe the phenomena and update the underlying parameters or variables or the means and standard deviations involved with them. But right now this is given to us, and hence we are using that to make our particular decision. Now let us convert this into decision tree as we have been doing earlier. That is, there is going to be a decision node. Out of this particular decision node, there are two decisions that contractor can take. If you see carefully, I have drawn a square box from where decisions are originating, with crash and without crash. Now after this, there is a chance node. This particular chance node is coming for the weather, where three possibilities are there. Weather can be good, weather could be average, or weather could be bad. So I would have good weather with 0.4 chance, I can have normal weather with 0.2 chance, and bad weather again with 0.2 chance. Similarly, a chance node comes here, and here I would have 0.4, 0.2 and 0.2. Now when weather is normal, again I have to account for two more parameters, that is mu is equal to 5 and sigma is equal to 3. Here I have to account for mu is equal to 15 and sigma is equal to 5. Here I have two branches further. One is that there is 90% chance no delay is going to happen, and 10% chance I have to deal with two parameters, 1 and 1 each. In second case, when no, I think we should say that this is for without crash program, this is with crash program. The line below decision is with crash program. 90% chance no uncertainty is involved, 10% chance uncertainty is involved, and the mean and standard deviation of those delays. Here I will go with 0.7, I would have 0.3, 1 and 1 being the parameter. So this is the tabulated version of entire information. This is the diagrammatic representation of entire information. Then I would talk about Cx, that is cost just because of delays plus launch of crash program. And again I would have another column where we will do all the calculations. When weather is good, no crash program is launched, no delay costs are involved, everything is on time, which is great. And we are not talking about profits here, because it is profits are the benchmark. It is the reduction in profit that we are talking. So benchmark cost of delays are 0. Then in second case, we get this particular number as 0.1 into Ex square plus Ex. We already did this calculation. So this number came out to be 8.4. In next case, this number came out to be 40. Again same concept, E of x square plus Ex, but with different values of expectations coming for this particular branch. Similarly, when we go below, when 40% times there are absolutely no delays possible, so the cost involved is 0 when weather is good, that happening is 40%. Now given that weather is normal, then some delays are going to happen. However, this particular cost would be jacked up by 10, because if you have launched a crash program and weather remains to be good, you have already paid for resource mobilization. There is no going back. You have taken a decision, you have to pay for resource mobilization, doesn't matter those resources are getting used or not. You might have purchased extra machinery, you might have procured extra laborers, and you might have entered into secondary contracts. Being a contractor, you can also subcontract some of the work again as the tender or the agreement documents allow, but here the cost has been incurred. Doesn't matter whether weather is good, bad or ugly now. So that 10 instead of 0, this number gets revised to 10 or it gets jacked up by 10. Of course, it would be disappointment if he or she deploys the resources, but weather continues to be good. But yeah, decision has to be taken keeping overall picture in mind, and that's what decision analysis does for us. Now, when we go to second case, let us say that 20% chance weather persists to be normal, then good. Then 90% chance that these resources will not come in use, but still you have deployed. So, cost of 10 will come into picture, and then 20% chance that the cost of 10 plus 1.2, remember we calculated this 1.2 earlier, that 1.2 cost has to be incurred. So, the total number comes out to be 11.2. Similarly, in second case, 70% chance extra resources were not needed, you still deployed 11.2 and 11.2. To make it convenient to understand, I will color all these things with their respective identifiers. So, here all the values correspond to the middle branch and all the values that I am showing in some other color, let us say I pick up blue, I show it here, that is coming in this particular color, because I have to multiply with their probabilities also. So, to avoid any confusion, I will do that. So, again all bad being rainy I am covering in blue, here I am covering the middle branch again with red, and all good I am covering with green. Now, if this is given to us, we can reduce its size a bit and continue with our calculations using same numbers. Now, I have to calculate what is the expected cost associated with decision, given certain decision has been taken and there are two possibilities of this particular decision. So, expected cost given that I do not launch a crash program is 0.2 multiplied by 0 plus 0.4 into 8.4 plus 0.4 into 40, and this number comes out to be 19.36 with a negative sign. This is a cost, so negative sign is important. So, this is expected cost given no crash program is launched. Now, when I move to the next part, expected cost when crash program is launched. So, I would have 0. I think this should be 0.4 by the way, chance of bad weather is 0.4, 0.4, 0.4, 0.4, this is 0.2 and hence this is 0.2. So, again 0.2 multiplied by 10 plus 0.4 which represents normal weather multiplied by 10 into 0.9, 90% chance that you will only incur cost of 10 when you have normal weather, plus 10% chance, so 0.1 you can incur cost of 1.2 units, and similarly for bad weather 0.4 into 10 into 0.7 plus 0.3 into 1.2. So, we get an expected cost of minus 10.192. Now, we started with so much information. Now, decision is clear to us that although prima facie launching a crash program appears to be an expensive choice, you would end up saving almost twice the money expectedly if the crash program is launched and more resource mobilization happens, because going with an assumption that weather is going to be good is against the odds based on the experience already. As a result of which, if you have to make an informed decision, it is wise to mobilize the resources, then not to mobilize the resources, even if mobilization of resources is resulting in larger upfront costs, but in long term you are going to have more optimal cost savings given that weather happens to be bad or normal and so on. So, this brings us to a conclusion of prior analysis where we bring in different sources of information, try to combine uncertainties of different type and come up with the decision. Here we didn't even use the distribution, by the way, we just focused on the first moment and second moment derivations to reach at the decision of choice. Even we can add next layer of complexity that delay itself can be normally distributed and so on, but the underlying probability and statistics may change, but the fundamental approach to the problem remains same. In subsequent modules, we will continue our discussion with terminal analysis. Thank you.